Hello students, welcome to lectures on complex numbers. In the last lecture, we discussed problems on nth root of unity, in particular cube roots of unity. Let me recall the last result we discussed in the class. That is, if T is an equilateral triangle with vertices A, B, C, which is oriented in the anti-clockwise direction, then it satisfies the following equation, that is A plus omega B plus omega square C equal to 0, where omega is the cube root of unity. And if it is equilateral triangle, if and only if it satisfies this equation, as well as it satisfies the other equation, that is A square plus B square plus C square equal to AB plus BC plus CA. Let us do a simple problem. T be a triangle with vertices, let us call it as Z1, Z2, Z3 in the complex numbers, with the property that their modulus are equal and their sum is 0. Then we have to show that T is an equilateral triangle. So, what is given to us is 3 vertices with equal magnitudes and their sum is 0, which is almost equal to the sort of cube root of unity property. But what we know is the cube root of unity, their modulus are equal, which is 1, but here it is not said that, it is only given that modulus are equal, which we do not know that whether it lies on the unit circle or more than the unit circle. So, let us try to visualize what is given to us. Since their modulus are equal, so they lie on a circle with some radius, we can call it as R. So, they are distributed on this circle Z1, Z2, Z3. What is given to us is their sum is 0. From this equation, that is given factor is the sum of these 3 complex number is 0. If we take the conjugation, still it is going to satisfy the same equation. So, take the conjugation, still it is 0, and this implies that it is Z1 bar plus Z2 bar plus Z3 bar, this is equal to 0. Now, use the fact that their modulus are equal. So, we can divide by mod Z1 square. If we divide by mod Z1 square, this is the value, anyway it is equal to the mod Z2 square as well as mod Z3 square. Then we get here Z1 bar divided by mod Z1 square, which can be written as Z1 into Z1 bar plus Z2 bar divided by mod Z1 square, which is same as mod Z2 square. So, this can be written as Z2 into Z2 bar plus Z3 bar divided by Z3 into Z3 power, this is equal to 0. So, we arrive to the following equation, which is 1 by Z1 plus 1 by Z2 plus 1 by Z3, this is equal to 0, and we can multiply by the factor which is Z1, Z2, Z3 as a common multiple for this factor. Then we arrive to the following equation, we get here Z2, Z3. So, we multiply this equation by the factor which is Z1, Z2, Z3, we arrive to the following equation, this is equal to 0. Let us call this as equation 1, and again from the given equation we have Z1 plus Z2 plus Z3 value is 0, then take its square, that is again 0. This implies that expand it, we get the expression Z1 square plus Z2 square plus Z3 square plus the factor which is 2 times Z1 Z2 plus Z2 Z3 plus Z3 Z1, this is equal to 0, and by the equation 1 this factor is 0. So, we get that Z1 square plus Z2 square plus Z3 square is 0. Let us call it as equation 2. From equation 1 and 2 we see that Z1 square plus Z2 square plus Z3 square, this is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. Okay. Now, let us recall the proposition which we proved earlier, that is, if you have a triangle with vertices ABC, this is equilateral triangle if and only if it satisfies the equation which is a square plus b square plus c square equal to ab plus bc plus ca. From this result we get that T is equilateral triangle. Hence, we have proved the given problem, that is, if Z1, Z2, Z3 satisfies this equation, then we proved that it is an equilateral triangle. Let us do another problem which has similar assumption, that is, we are given 3 complex numbers Z1, Z2, Z3 such that whose modulus are equal with the value as 1 and their sum is not equal to 0, but their square sum equal to 0, that is Z1 square plus Z2 square plus Z3 square equal to 0. Then we have to show that for any integer n greater than or equal to 2, consider the following expression, that is Z1 power n plus Z2 power n plus Z3 power n, calculate its magnitude, that will be always either 0 or 1 or 2 or 3. Okay. So, let us try to prove this result. So, first observation we will make is that the complex numbers Z1 square, Z2 square Z3 square are distinct. Suppose they are not distinct, what happens? So, which means that if let us say that Z1 square equal to Z2 square, then immediately from the assumption we see that Z3 square is minus 2 times of Z1 square. That immediately tells that modulus of Z3 is, whose square is basically 2, which is contradiction to our assumption that modulus of Z3 is 1. Okay. So, we observe that the given complex numbers Z1, Z2, Z3, they are distinct and they lie on the unit circle, which means that they are not like lie on a line. So, which means we can place a triangle with vertices as Z1, Z2, Z3, and the previous result will tells immediately that it is an equilateral triangle with the vertices Z1 square, Z2 square, Z3 square. Let me recall the previous result. We showed that if the magnitudes are equal and their sum is equal to 0, then we showed that the triangle with vertices as Z1, Z2, Z3 forms an equilateral triangle. Now, we observe that from this we observe that the triangle T with vertices as Z1 square, Z2 square, Z3 square is an equilateral triangle. And notice that one more say a note, we see that mod Z1 square and mod Z2 square, mod Z3 square whose modulus is 1. So, which means they lie on a unit circle and the corresponding vertices gives rise to a equilateral triangle, which means that the complex numbers can be connected through the omega. That is, we can obtain the one vertex by rotating 120 degree, that is multiply by the cube root of unity with Z1 square, and we can obtain the other vertex, that is Z3 square, multiply by further say omega to this quantity, that is omega square Z1 square. So, we can notice that omega can be written as omega power 4. So, which means the same expression can be written as omega power 4 multiplied with Z1 square. Here we keep as it is. Then we see that Z2 is given by square root of this element, which gives us plus or minus omega square Z1, and Z3 is plus or minus omega times Z1. Now, recall what we would like to calculate. We would like to calculate the value for Z1 power n plus Z2 power n plus Z3 power n. Now, calculate the expression, that is Z1 power n, Z2 power n plus Z3 power n. This is equal to we see that z1 power n can be commonly taken out. So, we get here 1 plus or minus omega square power n, again the plus or minus omega power n. Now, we need to calculate its magnitude. Since modulus of z1 is 1, so modulus of z1 power n is 1. So, we end up just calculate the magnitude of the following complex number, that is 1 plus or minus omega power 2 power n plus or minus omega power n. Thus, immediately what we can say is this is less than or equal to 3, but our intention is to show that their value precisely either 0, 1, 2, 3. Okay. So, which means that it will not take any other real number other than the integers, which is between 0 to 3. So, this can be easily realized, because we can see that for any value, well, this expression will be equal, that is omega power 2 n will be equal to omega power n. So, our question is, say when this will be equal, this will be equal only when omega power n is 1. So, it means that if I take n as integer values 2, 3 and so on, when it is 3 multiple, then you get the same value here, that is omega power 2 n as well as omega power n, you will get the same value which is 1. So, otherwise you get always here which is a different element, that is here you may get omega square, in that case you get here omega or 1. Similarly, so there will not be any equal element if n is different from multiple of 3. So, with this observation we see that we get only possibility here. So, possibilities are omega, omega square we need to sum, or omega with minus omega square. So, if I try to again recall, I am only focusing on sum of this expression. So, here minus omega, omega square, and other possibility minus omega square. So, under this possibility you can see that their sum will be always an integer. So, if I take everywhere the 1, so their sum one can easily verify that their sum will be only 0, 1, 2 and 3. So, I leave it as an exercise to make this verification. Let us do another problem. Compute the value of the following expression. Here again omega is the cube root of unity. So, we have to calculate the value for this expression. So, try to recall the properties of omega. One is 1 plus omega, omega square, this is 0, and omega power n, if it is multiple of 3, the power is 3 or 3 multiple of 3, then you get 1. in general we can write it as omega power n as 1 if n is multiple of 3. So, which means remainder if I divide by 3 remainder is 0, then the value is 1. Omega if n you divide by 3, if the remainder is 1, you get the value omega. Omega square if the remainder is 2 when we divide n by 3. Okay. So, now try to see some pattern here, that is if I consider the expression 1 minus omega square, this is equal to minus omega and remain 1 plus omega square is replaced with again minus omega. So, we get minus 2 omega. If I consider the next expression, that is 1 minus omega square plus omega power 4, which is nothing but omega. So, which is 1 minus omega square plus omega, the value is again replace 1 plus omega by minus omega square. So, we get minus 2 omega square. If I go the next expression, which is 3 plus 6, we see that immediately it is 1. So, the general observation is 1 minus omega power n plus omega power 2n, we will get the expression 1 if n is multiple of 3. And we get minus 2 omega if n is equal to 1 mod 3 and minus 2 omega square if the remainder term is 2 when we divide n by 3. So, with this observation, now the product now becomes simple. So, now what we can do is that by this observation you can combine 3 terms consecutively, which means that consider the first 3 terms product. So, the first 3 term product we get, which is first term is minus 2 omega and the next term is 2 omega square and the next term is 1. So, the value is 2 square, the remaining is omega cube, that is 1. If I take the other set of 3, again you are going to get the 2 square. By this observation, the value of the product is given by the following expression. Suppose n is multiple of 3, then we can combine 3 terms each other and then the product which we are going to get 2 square, and the number of times you are going to multiply is n by 3. This happens when n is multiple of 3. And when n is say multiple of 3 plus 1, then when we combine the three terms, then we will left out with one term which will comes from the term which is 1 minus omega plus omega square. So, the expression what you get is 2 square power, which is you divide by 3, take its quotient, and then there is a one more factor which we did not combine in 3 terms, which is minus 2 omega, and if n is say 3k plus 2, then with a similar argument we get 2 square. Here this is quotient of n by 3 multiplied with minus 2 omega and minus 2 omega square. So, now simplifying this expression, we get the value for the product factor. Now, let us try to study the geometrical object, which is like a straight line, and then we will go for a circle. So, first let us discuss what is a equation of a straight line in the complex plane. So, we will show that equation of the straight line in the complex plane is given by alpha bar z bar plus alpha z plus beta equal to 0, where alpha is a non-zero complex number and beta must be a real number. So, let us derive this. So, the general equation of a straight line in the Cartesian coordinate system is given by Ax plus By plus C equal to 0, where A, B, C are real numbers. To represent a line, either A or B must be non-zero. To add this condition, A square plus B square must be non-zero. Any pair of x y satisfies this equation. Now, trace this x y in the Cartesian plane, then we get a straight line. Now, for this pair of x y, we can associate a complex number, which is namely x is, say, let z equal to x plus I y, then the x is given by z plus z bar by 2 and y is given by z minus z bar by 2I. Now, recall what we have done. We are just doing the natural association of pair of element in the Cartesian plane to the complex number. So, given a pair of element x y in the Cartesian plane, we associate the complex number, that is x plus I y. Then we are able to see what is this x and what is y in terms of z and z bar. Now, if the pair of element x y they lie in a straight line, then it satisfies this equation. So, this implies that we get a times z plus z bar by 2 plus b times z plus z bar z minus z bar by 2 I plus c equal to 0, and just say combining the coefficient for z bar, we see that it is a plus I b by 2 and z times a minus I b by 2 plus c times 0. If we consider alpha as this number, then we can simplify further, that let say substitute alpha as a minus I b by 2, then we get z bar multiplied with alpha bar plus alpha z plus c equal to 0. Now, since a square plus b square is non-zero, that implies that mod alpha is non-zero, which is same as saying that alpha is a non-zero complex number, and where c is the another note say observation is. So, if I just summarize, alpha is a non-zero complex number and c is a real number. So, we get the following equation which describes the straight line in the complex plane. One can ask what is the slope of this line, and if we consider the slope of the given line, which is ax plus by plus c equal to 0, we get the slope as, that is m as minus a by b. You assume b is non-zero, then we could easily derive what is say slope of this equation in terms of alpha. So, slope of equation 1, we need to, since alpha is thus, then a can be derived by alpha plus alpha bar and b is given by alpha bar minus alpha. From this we could see that the slope m is given by I times alpha plus alpha bar divided by alpha minus alpha bar. So, from this standard equation one can easily derive properties of straight lines, like when the two straight lines will be parallel, as well as like to study perpendicular lines. This can be done by studying the corresponding coefficients of the straight line. Let me give it as an exercise, that is, we are given two straight lines. These two lines are parallel if and only if it satisfies this equation. If you recall, in the Cartesian coordinate system, you take the slopes of two lines, let us say m1 is a slope for line 1, m2 is a slope for line 2. If m1 equal to m2, then you will say that the two lines are parallel. Now, we are getting similar to that is alpha 1 bar by alpha 1. You treat that as some sort of slope in the sort of complex plane. If they are equal, then you get that it is parallel. And similarly, we have a other expression to describe perpendicular. So, we say that two lines are perpendicular if and only if this slope factor, which we denote by alpha 1 bar by alpha 1, that ratio plus the other slope factor, their sum must be equal to 0. Then we say that these two lines are perpendicular. So, let us try to study equation of a circle in the complex plane. So, what we studied is the simplest one, which is the unit circle, which is described in the complex plane by mod z equal to 1. So, radius is fixed, which is 1, then you trace the points, we get center as 0 and radius is 1. And if we try to write as a parametric equation, we get z equal to cis theta, that is cos theta plus I sin theta, with theta varies from 0 to 2 pi and modulus of z is 1. If I consider similarly center as origin and radius as r, which is described by mod z equal to r, and here you get the parameterization as z equal to r is fixed, and cis theta, where theta is varying from 0 to 2 pi. So, in this case we call it as, it is a circle with center as origin with radius r. Now, one could ask how to describe a general circle equation in this complex plane. So, if we call it as, so here the two cases what we see is that it is specifically centered at origin. So, here say center is fixed and whatever we described, the circles are only the radius is varying. If I try to describe any general, which means I need to just move the center to some other place. Okay. So, my interest to describe what will be the circle equation if I consider any point in the plane, let us say z0 as a center and let us call the radius as r. What is the equation for this? We have seen such a similar problem, that is, just say we need to shift this particular one to the origin. That is, like if I shift by z0, then the entire points going to move such a way that center is origin with radius as r. So, which means what is happening? It is simply the general equation of a circle can be realized as just shift the entire, say the given circle by z0. Now, we have moved this one to the origin, and what we described here is, if any circle with center as origin, then it is given in this parameterization. Now I have shifted my circle to the origin by z naught. Now this circle is parameterized by r cis theta, which is same as saying that modulus of z minus z naught is r. Here theta is from 0 to 2 pi. Now let us again look back this equation. The general equation of the circle, we are writing modulus of z minus z naught equal to r. Now I just squared it. This is nothing but with simple notation, that is, let us say that z naught as x naught plus I y naught, and let us consider the arbitrary point z satisfying this equation as x plus I y. Then modulus of z minus z naught square is given by x minus x naught the whole square plus y minus y naught the whole square equal to r square. Okay. So from this equation it is clear that from the complex number association to the plane, the Cartesian plane, we see that whatever equation which describes the general equation of a circle. So let us further examine this equation. So star can be again written as z minus z naught product with z minus z naught bar. So it is each one conjugation, that is r square, and what we get is the expression which is z into z bar, and other terms are z into z naught bar minus z bar z naught plus mod z naught square minus r square equal to 0. So now this looks little, say, view as general in the sense that we could see that the equation of the form z z bar minus z z naught bar minus z bar z naught plus some c equal to 0. So which denotes a circle provided with the following condition. So the equation, let us call it as say 1. One describes the circle if, what is the condition? Only we need to focus on C. C is nothing but C is mod z naught square minus r square. Now just trace back, we need to have just this term, the r square must be greater than 0, that is the only condition required to get the general circle with center as z naught with radius as r. So here C is denoted by this expression, and we see that r square, from this r square is given by mod z naught square minus C. This must be greater than 0, that is C is a real number, less than mod z naught square. Okay. So if I just summarize, 1 denotes the equation of the circle provided the C satisfies this condition. So, if C satisfies this condition, then we could say that this equation describes circle with centered at z0, but we need to manipulate to get the radius which is r. Let us discuss a simple problem. Suppose the set of all complex numbers satisfies this equation for some fixed alpha and beta and a constant k, then it represents circle if and only if the distance from alpha and beta whose square must be less than 2k. So, let us try to prove this result. Suppose a complex number satisfies this equation, then mod z minus alpha square plus z minus beta the whole square, this is equal to k, then it is same as z minus alpha multiplied with z bar alpha bar plus z minus beta product with z minus beta the whole bar, which is equal to k. Now, recall the previous result. We will have we need to represent a circle, we need to get in this particular form. So, let us try to simplify in this particular form. So, we have z into z bar, one factor from here, another factor from this expression. So, we get 2 times of z into z bar and minus z alpha bar minus z bar alpha and then plus mod alpha square, and other terms are z beta bar, z bar beta plus mod beta square, this is equal to k. And now, we have z bar. So, try to combine the coefficient of z, which is alpha bar plus beta bar minus z bar alpha plus beta, and let us collect the all constants mod alpha square plus mod beta square minus k, this is equal to 0. This is our constant like c, which appeared in the previous one. Now, the center point is nothing but alpha plus beta by 2. So, we see that z by z bar minus z alpha bar beta bar by 2 minus z bar alpha plus beta by 2, and let us call it as constant c. Now, this will represent a circle if and only if. So, this describes star is circle if and only if our constant c must be less than modulus of z naught square, where z naught here given by alpha plus beta by 2. So, which is alpha plus beta by 2 whole square. So, we have, so c is less than modulus of alpha plus beta by 2 the whole square. Recall what is c? C is mod alpha square plus mod beta square minus k, and we divided by 2 for the all expression. So, c is this, and then this is less than 1 by 4 mod alpha square mod beta square plus alpha beta bar plus alpha bar beta. Now, simplify this inequality. then we get minus k less than, we have say twice of alpha square mod alpha square plus twice of mod beta square. Once we bring to the right hand side, we get that minus mod alpha square minus mod beta square and plus alpha beta bar plus alpha bar beta. Now, multiply by the minus sign for both side, we get the reverse inequality, that is modulus of alpha minus beta the whole square, which is less than, one mistake, this is 2, less than 2k. So, this concludes that the desired result whenever z satisfies this equation and the constants alpha beta k satisfies this, then we get a circle, and whenever we get a circle by this particular equation, then the alpha beta k should satisfy this condition. Let me give you some simple exercises. Suppose z satisfies this equation where alpha and beta are complex number and k is a positive real number which is different from 1, then we can show that it represents a circle. And one more exercise, suppose a complex number alpha which lies in the circle, just notice that it is a circle centered at x naught y naught with radius as r, and alpha lies on the circle, and suppose alpha bar with 1 by alpha bar lies on the other circle with center is same but radius is 4r square. Then together with the condition that modulus of z naught square is given by r square plus 2 by 2. So, then we can determine the value of alpha. So, I will write down the answer. So, please verify it. Let me summarize. We first introduced a complex number system where we introduced the plus operation as well as the product operation. After that, we introduced the what is a modulus of a complex number and conjugation of a complex number, and then we studied several inequalities. After that, we studied nth root of unity and several properties and problems based on that. In particular, we studied the cube root of unity and several geometrical problems based on that. And the last, in this lecture, we discussed the several geometrical objects like straight line, circles, how it can be represented in the complex plane, and this gives a sort of illustration that any geometrical problem can be realized in the complex plane, and the problems in the complex plane can be transferred to a geometrical problem, and this gives some sort of a freedom to solve a problem in a different viewpoint. So, with this we end our lectures on complex numbers. Thank you.